Hello, everyone, and thank you for joining me today. We will talk about um, basically lecture number 2. We will discuss more in detail about SAGD. We will talk about the technology, and we'll use a real life example to showcase a lot of the kind of nuances associated with technology. And we're going to make some definitions in relation to thermal recovery schemes and then kind of dig into the data and better understand how those assets operate based on real life example. So the asset I picked today, you can see in the picture, this is asset that belongs to Athabasca Oil, and it's called Hangingstone. And you can see the facilities that you can see in this picture here, some of the surface facilities. You can see at the bottom, right there, you can see the pads, so where the oil production is taking place. And really everything is being back tied into the surface facilities that generate the steam and treat the emulsion. And here you can see the steam generation kind of facilities that are really a big requirement for the recovery scheme. So we're talking about Athabasca's Oil Corporation Hangingstone asset. So in the previous lecture, we finished to talk about the topic that where we showcased the injector well and the production well that looks like this, and we talked about some potential issues associated with the recovery scheme. And the question was, what do you guys think could be some of the issues? And what we realized is that, so if we kind of look at this from this view now, so from like a side view, we can draw the injector and producer this way. And what we talked about is that there is this concept of steam chamber development, where you basically you inject steam from here. So you get steam injection and you get oil production to the production well, which is here. And then we talked about steam chamber development concept, where the steam initially kind of looks like this, but then over time it gets bigger and the cavern gets really, really large in some point full of steam. And then we talked about some of the challenges associated with the recovery scheme, where you could see a scenario here, well, in most cases, where we talked about the concept that's called SOR. So steam to oil ratio, SOR, steam to oil ratio. And what we said basically is that when you get to kind of late life situation here, you have a very big cavern, and as steam is being injected, oil is getting produced, but over time, that steam to oil ratio, it tends to increase. And the way it happens on a chart, and we will look at some example, is that you will see something that basically looks like this over time. So this is time, this is SOR, and we have the situation where SOR is increasing over time. And really, it's a function of kind of the heat losses that's taking place to the overburden here, and expansion of the steam chamber laterally. And now basically for more steam, which is the S in the SOR, for more to produce more oil, you essentially need more steam. So you have that increase in SOR over time. And we talked about this challenge. And so at the end of the day, towards the end of the life of an asset, you need some kind of strategy that minimizes the SOR or reduces the SOR, which is also good for performance when it comes to economics, because now you can take that steam and allocate it elsewhere. But also, we talked about the fact that it's good for environmental performance because it's not as energy intensive. And the entire concept is co-injection of something that's called NCG, so non-condensable gas. So that's kind of where we ended. So let's overview this asset and see how we tie it back to the concept of NCG, SOR, and the entire recovery scheme that's called SAGD, Steam Assisted Gravity Drainage. And that's what this specific asset is utilizing as a technology. So what you see here, this development overview of the asset, you have Fort McMurray here. And you have something that's called CPF, Central Process Facility, where you have basically surface facilities to handle, the steam capabilities and production basically of the emulsion and gas flow that comes back to the CPF. And here we can see Hangingstone area in red. So development area that you can see in this little circle here. You can see some water pipelines, diluent pipelines, sales pipelines, fuel gas, and the project area, which is kind of overlaps where the development area is. So the project, the first team was in March 2015. And why I chose this asset is because it's fairly simple to understand. It has only 25 well pairs. When we say well pairs, we essentially talk about the injector and producer well pair. So injector and producer. So we say one well pair. So a well pair will be injector and producer. So we have 25 of those on this asset. So the location is 20 kilometers from south of Fort McMurray. So going this way, 5 production pads. So 5 production pads and 5 pairs per pad, which is 25 well pairs. 2 approved sustaining drainage areas, central process facility that again generates the steam capabilities and handles the gas and emulsion at the back to treat it, and off-site service utilities. So the infrastructure they have is fuel gas from TransCanada Pipeline, right here, Dilbit export to Enbridge Cheecham Terminal, and diluent from Interpipeline. So this is what our oil looks like, right? So it's kind of like a hockey puck in situ. It's very heavy oil, very difficult to produce, and that's why we use a steam-assisted gravity drainage process to drain that oil. And if we were kind of just to look at the rock at the back, you can envision basically the well pairs that we talked about. So injector, producer, and then chamber development to drain that oil by gravity if that rock was 40 meters high in its height. And then the liquid that drains, it's possibly looking like this, where you have oil and water maybe, or some kind of like foamy oil maybe because of NCG co-injection. Okay, so let's talk a little bit about the map here and kind of go deeper dive into the asset. So again, that development area here that we have is 7.3 kilometers squared. Significant amount of logs were required to better understand the asset. So those are the little logs, and the caprock cores. So one, to understand the integrity of the caprock. And what you see there, basically, this picture in the middle there, is the 5 pads that each of those pads have 5 well pairs. And those are basically 1, so AA, 2 AB, 3 AC, 4 AD, and 5 AE. And they talked about approved pad drainage areas. So again, 2 new development kind of pays that's going to be developed a little bit later, right? So they will decide how many well pairs they're going to put in each of those areas. So we have basically, from simplistic point of view, 5 pads, 5 well pairs per pad, so 25 well pairs on the 5 pads. So let's talk a little bit about bottom water. So obviously, when we look at the log, and you guys learned about the log already in your other classes, we have localized and not in direct contact with bitumen. Bitumen is the oil we're producing, separated by MIHS and or basal mud. IHS stands for inclined hydrolytic stratification. So those are the kind of non-permeable or low permeability geologies. We're going to talk a little bit more about that in this slide here, what really the IHSs, MIDI IHSs look like, and their criteria basically on how they're classified. But really important to understand that there are geologies around those pads that not necessarily shale blocks. So for example, you can see the bottom water here. We can have interbedded mud, which is a layer kind of above it, but then it sits kind of above the Devonian geology and defined as bottom water, which is what you see here at this kind of TVD there. And obviously, it could cause issues. So some of the issues could be that water, maybe you drilled a well here in the wrong location, and then you land in the bottom water, and now you need to produce the water, but you're there to produce oil, so you could have a problem potentially. And obviously, we have pockets here and here of water, so the operating team needs to really kind of keep a good look on the bottom hole pressure, so BHP bottom hole pressure, so it's maintained in such a way that the water doesn't have incentive to flow into the production well. And here below we can see the different kind of heights of the bottom water, so based on the color specified. So maybe in this section right here we have water that the bottom water at that height of like 3 meters, where by definition it's highly saturated, high pay water zone, where in other locations like PED AG we don't see bottom water, which is a positive. So here they're talking about minimal gas thickness and limited distribution within development area. Again, above the pays, we could have top gas. So in this case, they're talking about bottom water, and here we can have top gas. Again, through kind of geological formations and the way fluvial flows occurred and how things kind of evolved to be over the course of time, you do have partitioning where the heavier stuff settled first, so the bottom water, maybe higher density, settles at the bottom. Then you have kind of the oil sand, basically saturated with a lot of water, but also mainly in oil. And you have also partitioning in the top gas zones, which is what you see here, McMurray top gas base. So we need to be mindful of that. Why is that the case? You may remember we talked about our producer and injector and the chamber development. And guess what happens if, let's say, you're on PED AD and you produce one of those wells, and now in here you could be reaching a zone, and I will choose the red color because it's red here, that maybe has also top gas, like what you see here. And now what ends up happening is that the top gas enters the chamber and may create almost like an environment of kind of interrupting with chamber development. So where the chamber will grow, it will have maybe non-condensable properties, and then maybe not develop laterally as expected, or maybe there will be too much gas entering the chamber, which could result maybe in the operational conditions that are challenging for the pump or something like that. And again, in this example, we can see the gas thickness, 4 meters, 0 meters. So here it will be a little bit more prevalent, maybe here on PED AD not as much, but in overall fairly clean zone when it comes to the thickness of the gas top base zone on this asset. So this is a little bit more exciting slide where it really talks about the oil and how the oil is being classified when it comes to the phases classification. So obviously it's not just clean sand, it's not a sand box, it's not a sugar box. There are, through the readings here, you can see different basically readings of the pay quality. And really what you see here and the way they classify that is reservoir criteria, it's F1 to 4, and 1 meter less than F5. F5 is basically mud, over 70% as definition here by phases classification based on percentage of the mud. So if it's over 70%, then it's very low permeability, very low saturation of oil in those sections. And then obviously we have the breccia, which is variable. So F1 sand, 1 to 10, so fairly clean sand. Sandy IHS, so inclined hydrolithic certifications. So those are kind of barriers that look like this. And more muddy stuff, so IHSs where they have 30 to 70% of the percentage of the mud. And then what meets the criteria for reservoir criteria is the cleaner stuff, so 1 to 4, F1 to 4. We also have the net pay criteria here, as you can see, based on kind of a height, where the gross bitumen in place, GBIP, is based on the petrophysical criteria. It has porosity that's more than 27% and saturation SWT less than 50%. So, which is kind of how they define it here. And GBIP, again, final GBIP volumes include mid-lean zone. And obviously we can see kind of the net pay isopox here, where you have different pays. So we have really nice pays in those areas here. And that's why they developed those kind of the pads in this region and not maybe below in those sections, because you have really nice oil saturation in those sections that are closer to 30-40 meters, and that allows you to develop chambers that improve oil production and accelerate production for those sections where by definition they have more thickness to their pay. So this is seismic overview, where they take seismic and basically look at the section of what's going on. Not really going to go over it, but historically they've done a 3D acquired 3D seismic in 2011, 2012 to better understand the asset. And yeah, basically did the seismic to understand the geology and what's in place, in addition to coring the asset. And we talked a little bit about the coring, which is what you've seen here. So the idea here is basically how those pads and chambers evolve to be in this area, because you need to identify the geology where the wells are located. And obviously each one of those seen wells here, it's not really a well, it's a well pair. So you'll have a producer, an injector, and a steam chamber development, just like what we talked about before. I want to make a couple of critical definitions before we move forward, maybe that are applicable to our conversation here. And maybe I'll just kind of write them in this box right here. So one of the definitions I wanted to talk about that I think it's critical for understanding basically the asset, the kind of some of the terminologies will be I mentioned a couple of statements, right? So let's say fluvial, right? So that's will relate to stream, river, like overall flow, ancient flows that evolved in this geology. Stuff like erosion, right? So what will be an erosion, for example? Erosion will be a process by which material or rock or soil is worn away or removed by wind or water. I really wanted to define the concept of gas cap again, so just go over that. Oh, I realized I didn't type. So gas cap, like what does it mean to have a gas cap? Gas cap will be basically geological zone that contains a mobile, free-flowing gas phase. So kind of natural flow of gas, which is directly above the hydraulically connected zone, right, to an oil-bearing zone. So that's basically the layer between the steam, the chamber, kind of the oil zone and the gas zone. So for example, in this case, if we would draw the gas zone, it will be kind of here in this case. Another definition I wanted to go over, like obviously, when I talk about geology, we talk about science of Earth, including composition, structure, and kind of the origin of those rocks. When I talk about something like a GOR, so I think it's one important terminology to identify. So GOR, this will be something that's called gas to oil ratio, so GOR, and it's really unitless ratio of gas produced to oil produced from a well. But I think one at this point can identify why it's important, because if you're looking at the gas zones that we talked about, so here, and let's say you operating that pad AD, you will pay an extra attention to the GOR matrix, gas to oil ratio produced, because now if you're producing from the top zone, you now know that maybe you kind of compromised the operational chamber conditions, and you have to closely monitor the chamber development. The other metric that could be looked at, it will be called SOR. So we talked about SOR, which is steam to air ratio. WSR, so water to steam ratio, so how much water you produce relatively to steam injected. And that really fits in the criteria of the bottom water interaction. So let's say in this example, if we have pad AC right here, and we have some water zone at the bottom, what if you produce a little bit more water from what you injected, where ideally this ratio should be 1. Now you need to keep an eye that you maintaining bottom hole pressure from a perspective that you inject sufficient amount of steam to pressurize the reservoir or NCG, so then the water doesn't enter the chamber and basically reduces the oil production rate by kind of modifying the water cut in a sense. Okay, so as we continue looking here, we have a cross section here, and maybe I'll zoom in right there, right this. So this is A, and this is A kind of A dot, whatever. So we go from A and A semicolon or colon, whatever. So what you see here is basically the pays. Sorry, I'm running blank on some of the definitions here. And we basically see like a 37.5 meter pay. And then obviously based on the geological definitions, so like we defined before, breccia, you have sand, sandy IHS, muddy IHS, all that, you have different kind of geology partitioning in a sense through the height of the chamber. And what they're saying here is that there's the geology is heterogeneous, but you do have a 37-meter thickness to the sand pay here, 40 here, 38.9 here, 44 here, and 36 here. And obviously it's going through the pads to understand the kind of the quality of the asset and what to expect when it comes to chamber development, because not everything is going to be uniform and looking super nice, right? So before we go and cover the production rate, a couple more definitions just to kind of introduce. Obviously, we talked a little bit about the groundwater. The definition for that would be that it's really part of the kind of subsurface water that occurs beneath the water table in the soils and geologic formations that are fully saturated. If we talk a little bit about hydraulic connectivity, for example, and we'll talk a little bit about permeability and some definitions there. Hydraulic connectivity really is permeability of soil or rock to water, and it's really that K coefficient that depends on physical properties of formation and fluids, and describes in a sense the ease at which a fluid will flow through a porous material. So that's like hydraulic conductivity. And K is the rate of flow per unit cross-sectional area under the influence of a unit gradient that has dimensions of length cube over length square times time and or length over time, but should not be confused with velocity, for example. So that's kind of, I know I'm getting a little bit more technically here, looking at some of those kind of legacy and kind of definitions, I guess, to hydraulic conductivity. If we think about the hydrogeology, right? So what is the hydrogeology? And that really associated with the concept of the water kind of flows and stuff, right? So where was it? So the water stuff. So if we define the hydrogeology, it's the study of factors that deal with subsurface water and the groundwater that we defined earlier, and related to the geologic aspects of surface water as well. Groundwater used includes all water in the zone of saturation beneath the Earth's surface, except water chemically combined and minerals. And when it comes to hydrology, it's the science of waters of the Earth, their occurrence, distribution, and circulations, physical and chemical properties. So people that deal with hydrology, hydrogeology, as you can see, will be able to kind of better understand the bottom water and the water saturation in the core, and maybe if you have a top water situation, and really identify, even based on composition of the type of water that's being produced, what's the origin of that water. Is it from steam? Is it from the bottom water? Stuff like this. So often I would say words like, so here, let's write it down. I would say things like in situ. So I think it's an important definition before we continue. So in situ, that the word looks like this. What does it mean in situ? So in situ really is known as in place, like that's the meaning, in place. So, and refers to methods of extracting deep deposits of like oil sands using SAGD technology, for example. Um, and in situ technology in oil sands uses like underground wells. So that's all the stuff we talk about to recover resources with less impact to the land, air, water for oil sand mining. So that's what would be like a in situ definition. It's really, it means in place. And obviously, like when we talk about oil sand, it's very clear, right? So we have a sand, and we have so as you can see here, we have like a pay, like a thickness to it. um, that sand, you will find similar sand in like Mexico or something, or when you go on vacation on the beach, right? And that will be saturated with something. So that sand will be saturated with water and liquid, so water and oil, right? And the oil sand is really a deposit that containing heavy hydrocarbons, right? In this case, bitumen in the intergranular pore space of sand and fine grain particles. And so that's why the fluids are able to flow in a way through the sand and to be produced at the surface. So the typical oil sand comprises approximately a 10 weight percent bitumen, 85% coarse sand. It's not like ideal number. It could deviate, but that's kind of, from legacy studies, I guess you could assume that different fines like fraction consisting of silts and clays. So there's a lot of like intermediate geologies in those areas, and the whole region, or oil sands region, is it includes basically the oil sand region includes the Fort McMurray, Athabasca oil sands, sub-regional integrated resource regions, and others. So I think it's kind of important to be mindful of some of those definitions, just to kind of to get a better understanding of what I'm talking about. Pay, obviously, it's when we talk about pay, gross pay, we talk about the thickness associated with an oil-bearing zone, and permeability, which is another important term. Permeability, and we're going to see what's the permeability in this case, but normally really good permeability for rock that will have, let's say, 30-35% saturation. Really good permeability will be, let's say, 6 Darcy. But this is really, permeability is the capacity of porous rock, sediment, soil, or medium for transmitting the fluid, or the ability, let's say, of the fluid to flow through the porous medium. And it has dimensions of length squared. The value of permeability is very small, and it has dimensions length squared if you measure in centimeters squared, for example, right? So, but the value of permeability is very small. Therefore, more practical units are commonly used, like their Darcy, millidarcy, stuff like this. So in our case here, we use Darcy's because we have relatively very high permeabilities. So those could be between 0 to 6 Darcy's, and we're going to be seeing in our case what those are going to be. So before, and let's kind of review this table quickly to better understand those numbers. So if we think about, let's say, porosity in this case, right? So this is like porosity right here. Like what's the meaning? We see 35, 36, 34, 34.34, sorry, 0.34, so 34%. What's the meaning of porosity? So that's really the percentage of bulk volume of rock or soil that's occupied by uh, interstices, right? So whether isolated or connected, and those are kind of basically the porous medium, right? Like the bulk volume in a sense, right? And so what is that kind of those openings where from which by which the fluid can flow through? What do that mean? Those minute openings, right? Those little caverns, miniature caverns, which define that porous space, and where we define permeability, which is what you can also see here. So perm kh kv. So this is horizontal permeability. This is vertical permeability. We really defined it as capacity of the rock or the porous rock from that porosity of 35%. And the fluid to flow through that rock. So the ability, and which is measured in Darcy, as you can see in this example. So here in this case, we'll have 4.6, 5, 4.8, 4.5, and 5.3. So for example, if you look at the higher this number, the better it is. So the best, I guess, based on horizontal permeability here is PED AE. And based on also vertical permeability is also PED AE, right? But then you also have to be mindful of kind of like the other 5 pads, which each one of them will have 5 well pairs, so total 25 well pairs on the asset. What is the lateral length of those wells? So injector producer, right? So they will say 850 meters, 640, 750, 670, 830. The area of kind of operational area. So let's see some of the definitions here. So this will be 459,000, I guess, meter cube, square meters, square meters, and 347 square meters, 1,000 square meters of area. But now you have to really take into account the overall porosity and the saturation. So the saturation, how much is oil is saturated in this block. So if we have the sand here, we have certain saturation in that porous media, right? So you'll have, in this case, if you have 0.72, so 72% oil saturation, then you'll have like 28% from this, you'll have water saturation. If you have 73% SO oil saturation, then you'll have 27% or something like that of water saturation. You integrate the porosity, and you know the permeability, and you know the net pay, which we talked about. So in this case is net pay, 27 meters, 26 meters, 26 meters, 29 meters. And now you kind of have a better understanding of those geologies that we have in place right here, right? So what's going on in those cores? What does it look like? So we have a better understanding. Cumulative production. So that will be as of a certain date, right? So cumulative production, recovery factor of that production. So in this case for PED AA, for this time frame, it's 23%. So how much of that oil saturation within the porous media for that pad, what was the recovery factor of oil, right? And what you see here, you can also see EUR equals predictable bitumen in place. So this is the definition here. Estimated ultimate recovery of bitumen equals producible bitumen in place within the GBIP. So GBIP, we defined it prior to that in as gross bitumen in place, which was defined here, and that was based on the various classifications. So what we see here is basically the actual numbers of how much was recovered, right? So if we look at 23%, and we're looking at overall area, and we can calculate how much was originally in place, and we can see the cumulative production in cubes to 10 6, so it's in millions, right? And we can understand the recovery factor, that basically the estimated ultimate recovery factor, which is 50 to 70% right here, and how much was actually produced. So 23%, 39%, 17%, 22%, 25%. So this really means that there is some more time to go for this asset before maybe you need to drill newer wells. So this asset has some opportunity to to be further basically further produced before you need to spend the money. And this cumulative production is as of December 31st, 2023. So now we're in January 2025. So these numbers obviously increase on the recovery factor. So we have to be mindful of that as well. Now we have a couple more useful statements here, so let's go over them. So typical typical producer depth is 191 TVD. Initial reservoir pressure is 600 kPa at 190 meters TVD. Initial reservoir temperature is 8 degrees Celsius. And bitumen viscosity at initial reservoir temperature, now we're going to have to erase it so we can see. It's over 1 million centipoise, which is very typical. So over 1 million centipoise. And in the previous lecture, we looked at when you introduce steam injection and basically heat transfer to oil to be produced, that 1 million centipoise, over 1 million centipoise, let's say we have 10 here and we have 1 here, again, million centipoise, or a million centipoise here, and now 0.1 million centipoise. The graph looks something like this, right? So it was kind of like a curve to it over the temperature. The more temperature you get, the more viscosity reduction you basically see from that 8 degrees of initial reservoir temperature that was defined for the initial reservoir. Now, why is this important? Because during the course, we're going to be doing some simulation work. And that simulation work, we will be inputting initial conditions for what's happening in the reservoir. And so those initial conditions will be critical to kind of start calculating the flow rates and define them properly so we can kind of maybe forecast production. And again, GPIP, it's net GBIP plus lean zone without saturation constraint. And this was, again, the GBIP as defined. We covered it here, gross bitumen in place, right, based on the BRHES, NDIHS, MUD-IHS criteria, and F5 MUD, where everything like the reservoir criteria is F1 to 4. So the MUD is not cool. We don't want that. So let's look a little bit at some of the facts here. Cumulative production, we understood that. Well, spacing 100 meters, spacing between pads 130 meters. So that gives us some indications that now we better understand the distance between the well pairs here, but we also understand the distance between the pads themselves. So we're talking about 100 meters here and maybe 130 meters here. And the reason why it's important is because, let's say when you simulate it, you kind of have an orientation of where the wells are located and how they basically interact with each other based on the different phases of chamber development. We have definition. Volumetrics include 25 meter at heel and toe in the well pair. The full project area is defined, GPIP net hydrocarbon pore volume. So then they basically talked about the stuff they defined previously, and RF is the ratio of recoverable bitumen reserves and estimated bitumen in place in the reservoir. And yeah, let's kind of take a look at their production and try to better understand what took place. So again, the SAGD recovery scheme, you will have injector producer and chamber development. So chamber development, let's do it in red this time. So like this. So you inject steam here and you produce oil downward. So it drains by gravity because of the intermediate kind of heat transfer to the pay. And the more you rise, you get more production from the chamber. Okay, so what we see here is steam injection initially, which is in red. So in red, we get steam rate. That steam rate by 2017 went to about 7,000 cubes per day. So as you can see here, it went about 7,000 cubes per day and just peaked at those levels. So what did oil do? Oil did this. It went basically from here to here and peaked at this, I don't know, 1,200, 1,300 cubes per day. And now, if we consider SOR, it's really important. We can get the instantaneous SOR again on the monthlies, where we take this number here of the steam and this number here of the oil and divide the steam by oil, and we get the steam to oil ratio. What I really wanted to talk about is, if this is a hockey puck initially here, what happens in this zone that I draw here? How does the injector knows to communicate with the producer? We're going to be talking about this a little bit more in the upcoming lectures, but what's happening here is really called circulation. So you inject basically steam in both injector and producer, and you inject the water, hot water or hot steam, and you circulate those wells. So you're trying to create basically a connection, temperature connection here between injector and producer. And that's why you see a delay here when it comes to oil production from 2015 towards 2016, because you have this big increase in steam, but there is a lagging effect to the oil that's being produced. And so that really kind of expresses itself in the form of that circulation, where a lot of steam is injected initially, as you can see in this chart, and there's a kind of delayed effect for that oil to be produced. So we're going to be cover some of those topics in the upcoming lectures as well. A couple of things that are important to be mindful of. We're going to be doing more in-depth discussion about this chart, but let's kind of see what's going on. So you inject that steam here and you produce the oil, but there are other things that are happening. So you have essentially that ISOR that I talked about. So SOR, so that's the dotted line. So here that SOR is somewhat elevated, so it's about 5. The company, the team, by the way, did an amazing job cutting that SOR. If you look at the trend over time, it really declines towards the 3s, which is amazing. So that speaks to the efficient performance of the asset, especially considering that the oil rate, which can be seen here, was not sacrificed significantly. But steam was declining. But why? Because in purple, we can see the signs of NCG co-injection, which is in purple here, gas injection. So in late 2021, you can see big uplift in NCG right here. So in the purple line, and basically steam reduction. So you reduce the steam requirement, the in purple, the NCG injection going in, and now basically you go into this new technology scope where you haven't done before in the first 5-6 years of the life of this asset. Again, the asset itself is 5 pads, 5 wallpers per pad. And now you basically reducing the steam requirements, going from, I would say, 6,500 cubes to maybe like 4,200 cubes, as seen here. And you capturing the delta of value, which is really, really cool. So we're going to be talking more about this chart and other charts for other companies more specifically. But I think it's really important for this lecture to kind of start getting the idea of NCG co-injection, what does it look like, what it may look like for other assets, what this may look like for different geologies that we covered, for different recovery factors, different net of pay, like you do inject earlier, you do inject a little bit later, do you co-inject throughout the entire time? So we're going to be studying a little bit more about that. And here you see the porosity and saturation that will also vary from different asset to asset, and each and every one of you will have different asset to evaluate. This is just one asset as an example, but I think it's kind of a really important I guess introduction to what this may look like and what kind of considerations we need to consider as we continue in our class. So again, non-condensable gas, right? That's the main topic, NCG, non-condensable gas co-injection. So let's see, the company here communicates what they have done when it comes to NCG co-injection. So NCG co-injection has been expanded across all pads to help with pressure management and SOR reduction. So let's see if they were successful. SOR reduction took place, right? So they were successful. And the bottom hole pressure, so BHP, they don't report it in this slide, but their goal was to maintain it. So they say management, right? Management. Maybe they have a criteria where they want to manage it around a certain value, but I assume they wanted to maintain it because they inject that um, basically they inject that NCG reduce the steam. So what's the equilibrium? It's probably in maintaining bottom hole pressure. Maybe it declined a little bit. We don't know yet. We will simulate that in the future. But that's what the company basically communicates. NCG rate increased in early 2021 to assist with pressure recovery in the field following 2020 temporary suspension. Why did we have temporary suspension in 2020? Because of COVID, right? So the company wanted basically to assist with pressure recovery in the field with following 2020 suspension. So let's take a look here. So maybe what happened here is that we had steam cut, as you can see here, and then we had an oil cut. So during COVID, this asset was not producing. And what they're saying is that, hey, we're not just like maybe improving SOR performance and bottom hole pressure management, but we're also assisting by pressurizing back to previous pressures by co-injecting that NCG. Now, that steam wasn't allocated nowhere because we know in our picture, we know there's only 5 pads and 5 whelpers per pad. So that steam wasn't allocated anywhere. It was just not utilized. And so that NCG did a good job and maybe taught the team that now they can do something with that steam here with the triangle in the picture by utilizing it for further growth for the asset as they continue injecting NCG. And obviously, we see a very cyclical kind of manner of NCG injection, but continuous oil production rate, which is really positive. So, and again, I think it's also important to be mindful of the gas production rate in orange, which is also one of the consideration to think about because now the gas is also getting produced. So what does that look like? So this is something we're also going to simulate in our as part of our class. Once the field reached pressure target, NCG rates were optimized, and you can see here they reduced them. They optimized by reducing and then by increasing again. No adverse impacts observed. What does it tell me? That their forecast for oil production, which you can see here in green, was not impacted, right? So if they didn't have any damage associated with NCG co-injection, that means that that forecast was made for SAGD and similar recovery was seen as part of NCG co-injection. Continuing vertical temperature growth at observation wells. So they're continuing healthy development of the steam chambers. So I think if we were kind of to look back, so what did we cover today? And do a quick summary. So we looked at the Athabasca Oil Sands asset called Hangingstone. We talked about chamber development, SOR in the context of NCG. We defined what whelpers are and how they're utilized. We understood where CPF is located relatively to the development, and we understood a little bit more about the asset and where it's located. We talked about the structure of those pads and the whelpers and the location and what was done to end up in this area by coring the lease and better understand where to develop the pad seen in the picture. We also learned that there is some bottom water in the asset, but it's not really significant, right? So we have pads AF, AE. In the future, I guess AF will be the pad developed, AE, AD, AA, AB, and initial sections here from pad AB, a little bit here on AC, but it's not, the bottom water is not everywhere, all over the place. We talked a little bit about minimal gas thickness that they have on the asset, but this gas thickness could be more serious in other assets. But here, it's mainly around this AE kind of location when it's located at the heel area of AE and kind of central AD towards kind of AB and the thickness associated with that gas. We talked a little bit about the bitumen pay classification, reservoir criteria. What does it mean, right? How incline hydraulic stratification plays a role in gross pay integration to better understand the the producible oil and how it's being classified. We also looked at some seismic overview. We didn't go in depth. I chose that, but we did learn that the spacing between the well pairs is 100 meters. The spacing between the well pads is 130 meters. We also looked at the pads AE structural cross sections going from northwest to southeast, and we learned that 40 meters, 44 meters, 36 meters, and the various geologies in place in that cross section. We looked at production history, and we tried to better understand the various kind of matrices or the different kind of variables that we need to be looking at and different readings and better understand those. So water to steam ratio, cumulative steam to oil ratio, instantaneous steam to oil ratio, steam rate, gas injection rate, water rate, well count, which barely changed, right? It's about 25. Oil rate and gas production rate. And finally, we talked about a table with reservoir properties to better understand the asset and the activities that were done when it comes to non-condensable gas co-injection, NCG, which is the core topic of this basically project. So, long story short, 52 minutes of lecture 2. So I think we covered a lot of ground. And I will email the team about the next steps and activities for the second week and what we're going to be up to next week. Obviously, you guys, what you're doing right now is you're doing a lot of research about SAGD, trying to get familiar with the different assets and how these assets operate. And so hopefully this example from Athabasca Hangingstone asset gave you a good overview of kind of how to look at things and better kind of contextualize the concepts that we're learning about in this course. All the best, guys. We'll talk soon. Thank you.